Hi, Brianna.
Sawa.
Yeah. Okay. Yeah, we'll see. Okay, guys, I'm going once again. Sanibonani Brianna and Cindy. Cindy Kubera from where we left off yesterday, which is what we're dealing with. Under the topic of work, energy and power. Work, energy and power, wherein we said to you are looking at the concept of the work done by a constant force. But just to give you a recapture, especially of the formulas that we've dealt with. Just to recap on what we spoke about yesterday, we spoke about the formulas that we use. So we define the work done as the force, product of the force and the displacement, times the cosine of an end between the force and the displacement. That was the first formula, the definition of work that we looked at yesterday. So that's the first thing that we need to do. Then we went on to the work energy theorem, wherein we've said work done by the net force is equal to the change in kinetic energy of an object. This is the second formula that we looked at. Then we went on to looking at work done by all the non-conservative forces acting on an object. Sawachaza non-conservative forces such as mention foot. And then we've said to you this will be equal to the change in kinetic energy plus the change in potential energy. We'll speak now about this. Last but not least, we spoke about conservation of mechanical energy. When there are no non-conservative forces, we said mechanical energy is going to be conserved. And we said if I've got any 2 points, mechanical energy at A will be equal to the mechanical energy. These were the formulas as far as energy work is concerned that we mentioned about. These were the formulas that we have mentioned when we spoke about. Let's speak about this, especially the last two. This formula here, there are certain few things that you need to look at. One, there must be the height. An object must be moving from a certain height and then down the incline or something like that. But I need to first have the height. So if I check, am I given the height? If the answer is yes, then step number 2 is, do I have non-conservative forces? Your conservative forces include the likes of, I need to be having a frictional force, or I need to be having the applied force. Any one of the non-conservative forces, or it could also be the tension force. If I've got one, firstly, before I can use this formula, I need to check, is there a difference in height? If the answer is yes, then the next question will be, do I have one of the non-conservative forces, which could be a frictional force, which could be an applied force, or which could be the tension force? And if the answer is yes, then you are ready to use this formula, to apply this formula over there. Whereas this one, again, with the conservation of mechanical energy, you still need to have the height. The object needs to have, there has to be a difference in height. And then secondly, as opposed to that one, here you need not to have, there must be no frictional force. There must be no applied force. And there must be no tension. There mustn't be anything that can be pulling this object. There must be anything that is slowing down this object. So notice the difference between the two. They look almost the same. The two formulas look almost similar. The conditions look almost the same because we need to first have a height, but the story changes. If there is a friction or the applied or the tension force or the combination of those forces, if they are present, then we cannot apply the conservation of mechanical energy. So notice that these are the conditions under which we're going to be using these formulas. So as we are moving on to solving the problems, I'm going to be reminding you guys over and over about these conditions so that you are very well aware of that. Then we spoke about average power. We said power is the rate at which work is done, W over delta T. That is the first formula we get. Last but not least, we look at the formula. Power is equal to the applied force multiplied by the constant velocity. We said with this one, an object must be moving at a constant velocity. So the object needs to be moving with a constant velocity for us to apply that formula to calculate the power. So these are the formulas that you need to know about. But over and above this, you need to know your Newton's laws of motion. Newton's laws of motion. So there are other keywords that we need to be looking at. There are certain keywords that we also need to be looking at. But most important, let us look at what we're going to do. How do we solve the problem that involves this? So the advice would be, make sure that you draw a free body diagram. Showing all the forces actually on the object. So we need to identify these forces, then draw a free body diagram. And then secondly, once we have done that, we need to look at the angle, identify the angle between each force and the displacement. Each of the forces and the displacement. And this is what we need to look at. And then next, once we've done that, then we can calculate the work done by each force. Calculate the work by each force. But most importantly, remember that what we have said to you yesterday. We have said that when theta is equal to 90 degrees, then the work done by force is 0, such as the normal force. Work done by the normal force is always 0. Why? Because the normal force is always perpendicular to the surface. It is perpendicular to the displacement. So cos of 90 degrees is equal to 0. And that is the reason why the work done by the normal force will always be 0. So those are the few things. Draw a free body diagram, identify the angle between each force and the displacement, calculate the work done by each force. That is what we're going to be looking at. Then we're going to look at certain keywords, that such as what? When they are telling you that when the velocity or speed is constant, if they are telling you that the object is moving with a constant velocity, then what happens? Then this is what you need to know. the net force acting on an object will be zero. The work done by the net force on an object will be zero. So these are the key words that you're going to be looking at, and these are the things that you're going to be looking out for when you start solving these problems. So this is what basically we have spoken about yesterday. This is what I've spoken about. From the formulas, these are all the formulas that you need to know as far as energy, work, and power is concerned. But remember that we are speaking about the work done by a constant force. Therefore, you're also going to need to know something about the Newton's laws of motion, which governs the manner in which we handle the forces. And with that, unless there are any questions, we are going to be looking at this question too. And we're going to be looking at these pointers that we mentioned earlier on. We want to look at this question too. For 15 marks, very simple question, but we need to be very careful when we read about this. So here's our question 2. So here's the question 2. Chichi, you were not there yesterday. I got your message. But let us look at what we're going to be speaking about here. So here is question 2, and then we look at these pointers that we've spoken about. You're going to be trying to apply this technique here or this strategy here, and also remember that you're going to be looking at these two, especially these two formulas where there is a height. So let us look at this question 2 and see. 5 kg block is released from rest from a height of 5 meters. Already we have the height. So we already have the height. So now the next thing will be for us to check. Is there any frictional force or is there any applied or tension force? They are saying that height of 5 meters, frictionless incline, slides down a frictionless incline. There is no frictional force. And then it is sliding. When something is sliding, then it means that there is no applied force. It is sliding freely. Nothing is pushing it, nothing is pulling it. It's sliding freely. So we do not have the frictional force, we do not have the applied force, we do not have the tension force, but we do have a height. So it looks like this is a condition that is satisfied. We have the height, there is no friction, no applied force, no tension. Therefore, for that particular portion of the track, mechanical energy is going to be conserved. I don't know if you guys are still with me there. So notice that we do not have the frictional force from when the object starts at this point, and also the velocity of the object at this point. It's been released from rest. Remember, released from rest. So the velocity at that particular point, and the initial height is 5 meters. So it is going to slide down until it reaches point P. Now let us hear what they say. It slides down a frictionless incline to a point P as shown below. Then moves along a frictionless horizontal plane. Frictionless horizontal portion PQ. And finally moves up a second rough inclined plane. The second inclined plane is rough. There is a height. Notice that. We have a height here. But it's a rough surface, which means there is a kinetic frictional force acting on this. So for the portion from Q to R, we are going to be looking at the work done by all the non-conservative forces. I hope you guys are still with me on that particular point. Then as it comes to a stop, 3 meters above the horizontal point R. So that is what is happening, guys. Remember what they are saying to you. When we look at the object as it slides here, we can see that there is this force, gravitational force. We said we need to identify the forces. We've got a normal force. And that is about that. There is no any other force acting on this. We've got the gravitational force and the normal force acting on this object as it moves down. But when the object reaches the portion PQ, they've said it's a frictionless, horizontal, frictionless. PQ is frictionless. Once again, there is no applied force, there is no frictional force. We only have got these two forces, the normal force and the gravitational force, both of which balance each other out. The net force from P to Q is 0. Net force from P to Q is 0. I hope you guys are noticing that. Any questions so far before we start? Frictional force, a non-conservative force between the surface and the block, is 18 newtons. So they are referring here to the portion QR, because that is a rough section over there. So when the object reaches this portion here, it will still be having the gravitational force, it will still be having the normal force, but over and above that, remember it is moving up. Frictional force will be opposing the motion, so we'll be having 3 forces when the object is moving. So notice there are 3 different sections, from the top to point P, then from P to Q, and then from Q to R. There are 3 different sections that we're going to treat differently, because they are different altogether. So let's look at our first question. Using energy principles only, calculate the speed of the block at the point P. What do we know about this point P? We want to find the velocity here, but we know that the height from the top to there, we are now at the bottom of this, so the height is 0 at the point P. And what else did we say? There is a height, there is no applied force, there is no frictional force, there is no tension force, under which we have said, when those conditions are satisfied, there is a height, there is no frictional force, no applied force, no tension, then mechanical energy will be conserved. And that is exactly what we're going to be doing here. Conservation of mechanical energy. That is what we're going to be applying. So notice that we're not just picking up any formula. Look at the conditions first. Conditions, we need to have a height. There must be no frictional force, no applied force, and no tension force. Then we can say the mechanical energy at the top will be equal to the mechanical energy at the bottom. And remember, by very definition, mechanical energy is the sum of the kinetic energy and the gravitational potential energy. At the point P. So we are starting from the top. Our initial point, which is at the top of the ramp. When we given the mass of our object, it's 5 kg. 5 kg. But this thing was released from rest. At the top, the velocity is 0. Mass is 5, G is 9.8. At the top, the height was 5 meters, released from the height of 5 meters. So we substitute the 5. We do not know the velocity at the bottom. That is what we want to calculate. And then the mass of our object is 5. This is 9.8. And the final height is 0. So we do not have to worry about these that are multiplied by 0. This will automatically be 0. This will automatically be 0. But what we need to be working out, I need you guys to assist me with the calculators here. 5 times 9.8 times 5. Can you give us the answer there? 5 times 9.8. Yes, Cindy?
245.
Can you repeat that again?
245.
245. Thank you, Cindy. Right, half of 5, I think we all know it's 2.5. VF squared. Then we divide the both sides by 2.5. Divide the both sides by 2.5. We still have a VF squared. We take out the square root. And I need you guys to help me once again. What is the square root of 245? Divided by 2.5. That will be the velocity of our object. Yes, Dave, can you help us again?
9,89.
89 meters per second. So the block will reach the bottom of the ramp moving at a speed of 9,89 meters per second. Notice that now. Notice that from P to Q, the surface is frictionless. There is no net force acting on this object because the normal force and the gravitational force, they cancel each other. One is pulling up, the other one is pulling down. So that effect cancels each other out such that there is no net force from P to Q. As the object moves from P to Q, the net force will be zero. And if the net force is zero, the velocity of your object at P will be the same as the velocity of your object at Q. We are reversing this, Cindy. We are reversing this point, the last point, bullets that you have mentioned here, that when the velocity of an object is constant, the net force will be zero. The opposite is equally true. When the net force acting on an object is zero, then the object will be moving at a constant velocity, such that between those 2 points, any 2 points, wherein the net force is zero, the object will have the same velocity. And that is the case. Moving from P to Q, the net force is zero. And if the net force is zero, it will follow that the velocity at P will be the same as the velocity at Q. Any questions so far? It is for that reason that answers your question 2,2, GG. When you say that if the velocity at P is the same as the velocity at Q, it follows that the kinetic energy at P is the same as the kinetic energy at Q. The reason being, it's because the net force acting on the object is 0 newtons. That is the reason. Net force acting on an object as it moves from P to Q is 0. Okay? So it is for that reason. I hope you guys are paying attention to that. Notice that we can actually expand from this to say that when the velocity is constant, the net force acting on an object is 0. The work done by the same net force will also be 0. But most importantly, the kinetic energy of an object will also be constant. Kinetic energy of an object will remain constant, provided velocity is constant. If the velocity is constant, kinetic energy is constant. If the kinetic energy is constant, net force will be 0, and the work done by the net force will also be 0 joules. So I hope you guys are with me. Any questions before we move to the next 2,3? Chichi, you were not there yesterday, so I hope you're going to be able to catch up. But I've sent you the work that you have done yesterday. So if you can try to go through that. But should you have any question, feel free to ask. Explain the meaning of the term non-conservative force. The non-conservative force, we've explained that. But most importantly, our explanations and definitions, let us also emphasize on that. We will always be relying on the examination guideline document. So for all your definitions, for all your explanations, for all your principles and laws, we're going to verify we get to this. So this is where they are saying, bullet number 2, conservation of energy with non-conservative forces present. Bullet number 2, define a non-conservative force as a force for which the work done in moving an object between 2 points depends on the path taken. So that is what we're going to be looking at. So you're not going to be applying any other definitions, but the one that is stipulated here. It's a force for which the work done in moving the object between the 2 points depends on the path taken by the object. And then notice that here, there are 3 different paths. The first path was of this orientation, that is the first path. The second path was of this orientation. And the last path was of that orientation. These are 3 different oriented paths. Your frictional force will depend on the path. In what sense? if this was a rough surface and the object was moving to the right, the frictional force was going to be pointing towards that direction. But once the object is here and it's moving up, the frictional force changes the orientation, and then it just got that. It depends on the path followed by the object. So in this particular instance, to explain this, we refer to our examination guidelines to say that it is the force 2,3. Non-conservative force is a force for which the work done in moving the object between 2 points between any 2 points depends on the path. On the path followed by the object. So that is what you're going to be doing. And remember that at any given point in time, you are studying each topic in conjunction with this document, examination guidelines. Because the exam guidelines gives you exactly what will be examined. So everything, the formulas, the definitions, we're always going to be studying, and keep this with you at all the times so that you write the correct definitions and the acceptable definitions. Anything that is not, as far as definitions are concerned, anything that is not from this document will be marked wrong, unfortunately. So your definitions, please use this document, examination guidelines. Now we go on to question 2,4. Calculate the angle theta of the slope QR. So how do we go about doing that? How do we go about doing that? I think the easiest way would be if we can calculate the displacement from Q to R. If we can find this displacement from Q to R, and then we can apply our trigonometric ratios. Let me write on a clean page. I think the easiest way for us to do this would be, remember you are given this, and this is the angle. This displacement, if we can calculate this displacement, it should be easy for us to find the angle theta, because remember that from mathematics, this is the opposite side and this is the hypotenuse side. So if I've got opposite over the hypotenuse, that is a ratio defined mathematically as a sine of the angle of inclination, which will be 3 meters divided by delta x. So therefore, we need to find the displacement that the object will move. So once we have delta x, we can easily find this. That is our goal now. That is our mission, to find that. So in our finding that, remember, we're gonna you've got the normal force. Normal force is not doing any work on this object. This was a rough incline. I'm not sure that it's a rough incline. There is a kinetic frictional force, and you've got the height. So we have said to you, when there is a height of an object and there is a frictional force, either friction or applied or tension force, or the combination of those forces, then we're going to apply what we call work done by all the non-conservative forces. All the non-conservative forces. Pay attention to that. This is the work done by all the non-conservative forces collectively. In this case, we have 3 forces acting on our object. Gravitational force is a conservative force. So it will not form part of this formula because gravity is a conservative force. Work done by the normal force is equal to 0. So we're not going to bother about normal force. The reason being because it is perpendicular to the displacement. This is the non-conservative force that we are going to factor in this formula, because frictional force is a non-conservative force. We're not going to look at the work done by the gravitational force. The reason being Because the gravitational force in this case is a conservative force. We are looking at the work done by all the non-conservative forces. And the only non-conservative force in this particular case is the frictional force. So we have our free body diagram. We then went on to say to you, when we're looking at this label, as we said, after having this, then identify the angle between each force and the displacement. In this case, our concern is only with the non-conservative forces. So let us look at this. There is a displacement, this vector, and there is a frictional force in the direct opposite direction. The angle between those two is 180 degrees. The angle between the frictional force and the displacement. So in our calculating this, we are looking at the work done by the frictional force because it is the only non-conservative force present. We can expand on this change in kinetic energy, half mvf squared minus half mvi squared. This being the change in kinetic energy, plus the change in gravitational potential energy, final height minus mg hi. This being the change in gravitational potential energy. So we've just expanded on this formula. Now remember, the work done by any force will be the magnitude of the force multiplied by the displacement multiplied by the cosine of the angle between such a force and the displacement. So in our case, we are looking at the frictional force. Yes. So let us go back now. We were told about the magnitude of this frictional force. The frictional force, and they even told us that it's a non-conservative force between the surface and the block is 18 newtons. That's a magnitude of our frictional force. So we take that magnitude as it is, we substitute there, 18. We do not know this displacement, it's what we are hoping to calculate. We have just said that the angle between frictional force and the displacement is 180 degrees. Furthermore, remember we have calculated, we are starting from this point. So this is our initial point. We have calculated the velocity at a point Q, which is the same as the velocity at a point P, 9.89 meters per second. So at this point, the velocity is 9.89 meters per second. And they have said to you, the object comes to a stop 3 meters above the horizontal point Q. So at this point, at a height of 3 meters, the object will come to a stop. The velocity there will be 0. The velocity there will be 0. So notice that now, when you substitute here, the mass of our object is 5. At the point 3 meters above the ground, the object comes to a stop. But at the bottom of the ramp, where it started now, before climbing up the rough incline, it was moving at a velocity of 9.89, which must be squared. Where it ended, the mass is 5, this is the, where it ended, the height is 3 meters. Where the object started, 9.8, it has started from the ground. So the height is 0. Initial height is 0 because we are starting from the ground. At the ground level, the height is 0 at this point here. Initial height is 0 meters. At that point, Okay. Guys, sorry, the network is giving us some issues here, but it looks like it's sorted. Can you please confirm if you can hear me? Is the audio still clear? Am I still audible? Because I don't know what happened to the network. We just got disconnected. Guys, can you still hear me?
Yes, sir.
Okay. All right. I'm sorry about that. I don't know what happened. We just got disconnected for some reasons. But I need you guys to assist me with these calculations. We can omit these, the ones that I have in zero, these terms that I have in zeros. We can omit them because we know this is zero and that is zero, so we don't have to worry about that. If you can kindly punch this on your calculator, minus half of 5 into 9,89 squared, plus that. Okay, this side we've got 18 plus 180. We know that it's going to be negative 18 delta x. So if you can kindly punch this on your calculator for me.
Maybe.
Guys, what is the answer here on the right hand side of the equation? Cindy, 440,
440,4363.
Omar,
4363.
4363. Okay, that's about 5. Is it positive? Is it a positive answer?
Sir, with the 0 minus, so it's negative.
Pardon?
Negative.
Yeah, it has to be negative. Because work done, remember, work done by the frictional force will always be negative. And there isn't being frictional forces opposing the motion. So this can never be positive. It's a negative 440. Then we divide both sides by negative 18. Divide both sides by negative 18 to find the displacement. What is the answer there?
For 7.
Didn't get that.
24,47.
That is meters, that's your displacement. Boom. So there we have it. So like we have said, guys, remember the intention was that you find this displacement so that we can end up calculating this, which we have said is h over delta x. The height of our incline is 3. The displacement that the object will move is 24,47. So when we find this angle theta again, it will be the shift sign, the arc sign, shift sign of 3 divided by 24. So we start with the shift first. The shift on your calculator, then sign. Shift, then sign. What do we get? Cindy, what's the answer there? Or Chinonye? Or even Rianda? Remember, we start with the shift here. This is arc sign, arc sign. Start with the shift, then sign, shift sign, then of that number. 6,92. Are we all getting the same thing?
7,04.
7,04. So why are your answers different? Can you please confirm this again? Shift sign, someone is Lindy has got 6,92, and then when I'm saying 7,04, which is which? Anyway, can you confirm? And Chinonye, can you also confirm your answer once more? Lindy, are you still getting a 6,92? Now, guys, so what do I write here? Because I'm waiting now, we can't be stuck. You can't just calculate and tell me what is the technique spread.
7,04, sir.
And please make sure that your calculator is set to degrees. There has to be a D always related to the you do. Make sure that it's on degrees. It mustn't be on radians or the gradients. It must be strictly on degrees. Otherwise, you're going to be getting some funny looking answers, and that will be a very huge problem for you. Make sure on the screen, at the top of the screen, you see a symbol D for degrees at the top of your calculator, or the screen of your calculator. Please do make sure. So the answer here we found it to be 7,04. I hope you guys can see here. So the technique here, we apply this few pointers. That's a technique that you're going to be following. And we're done with this question. So let's look at question 3 once more. We still going to be applying the very same techniques that we have been applying. So you start to see as we move forward, you start to see the pattern then that a lot of these things are actually common. So as we're working on this, look at how we go about solving these problems and look at the pattern. Leander. I didn't get your question. I don't know if you had a problem. Okay, Leander, you can always use the chat option to type down the question. So we have the chat. So please make use of that function. I can see on my screen whatever I type here. Right, as we move to the next question. The diagram below shows a heavy block of mass 100 kg. Your line is very defined. Can you please try to type or rather leave the meeting and join immediately again because your audio is very bad. So if you can maybe leave the meeting and join again, we will wait for you. I hope you help me with that. Leave the meeting and join again. It will make your audio to be better because currently your network is very bad. Okay, the diagram below shows a heavy block of mass. You can type down your question, Rianda, because the audio is not working. Use the chat option to type down the question. A heavy block of mass 100 kg sliding down, excuse me, a rough 25-degree inclined plane. Notice that it's a rough inclined plane. So we are noticing that, and then the block is sliding down. A constant force F is applied on the block parallel to the incline as shown in the diagram so that the block slides down at a constant velocity. Slides down at a constant velocity. So you are paying attention and you remember everything that we've discussed about constant velocity. And we have said to you that when the object is moving with a constant velocity, the net force on such an object will be 0. And the work done by the net force. So those are the two things that we need to remember as we are working towards this. So keep that in mind. Magnitude of the kinetic frictional force between the block and the surface, 266 newtons. That's a frictional force. So before we go on, The question 3.1, I think you can start to see the patterns now that I'm speaking about. Question 3.1 is similar to question 2.2 because they speak about friction is a non-conservative force. What is meant by the term non-conservative force? We already have encountered a similar question previously. So by now, we know that it means that question 2.2, so it was that 2.3. We've answered that and we said that it means that it is a force from which the work done in moving the point, the object between 2 points depends on the path. So this is a repeating question. And by now, I think you can already see that such a question is likely to repeat itself. It could be the non-conservative force, or they can ask about the conservative force, but there are patterns that you start to see. There are repetitions that you're already starting to see. So this question is coming up again for the second time. And then we've already answered it. Question 3.2. A learner states that the net work done on the block is greater than 0. Is this learner correct or not? And how can we justify that? Anyone who can assist us with that? We have just spoken about this. The object slides down at a constant velocity. So what do we know about the net work done on an object when the object is moving at a constant velocity? Anyone who can assist today? Is the learner correct or not to say that the work done will be greater than 0? Is this learner correct? Hi guys, we just spoke about this. We have just spoken about this a few minutes ago. Cindy, is this learner correct to say that the work done will be greater than 0? The net work done on this object or this block will be greater than 0. Is that correct? No, guys, no, guys, we're not paying attention. We just spoke about this a few seconds ago. When the velocity is constant, net work done is not greater than 0, but it is exactly equals to 0. So this learner cannot be correct because we just mentioned it, that when the object is moving at a constant velocity, then the work done cannot be greater than 0, but it is equal to 0. So the answer is, it's a big no, a resounding no. It cannot be correct when you're moving at a constant velocity, but rather, how can we use the physics principle? When the net force, when the object is moving with a constant velocity, it's moving with a constant velocity. The net force on such an object will be 0. That is the first thing that you say. Which physics principle states that? Which physics principle? Because this is not just a statement that is floating within the thing here. It's a physics principle. And that is Newton's first law of motion. Newton's first law of motion speaks about an object that is either at rest or moving with a constant velocity. It says so exactly that when an object is moving with a constant velocity, then the net force on such an object will be 0. And if the your network is bad, please try to leave and join the meeting again. Leave the meeting and join again. It will solve your issues. That will solve your issues. Because you are being delayed, you are taking us back and we don't know what you are saying. We can't hear what you are saying. Leave the meeting, join again. That will sort out your technical problems that you are encountering. So this is what the level suppose. It cannot be greater than 0, but it will exactly be equals to 0. Constant velocity, 0 net force. 0 net force, 0 net work done. Simple as that. It is as simple as that. And this is in accordance with the Newton's first law of motion. Newton's first law of motion speaks about an object that is either at rest or moving at a constant velocity. That is what this is all about. And then we move on to the question 3.3. Calculate the magnitude of the force F. How do we do that? We need to have a free body diagram here. This is where now the issue of a free body diagram comes into picture. So we look at this object on this inclined plane, and then we try to identify all the forces and draw the free body diagram. We already have seen that there was an applied force, which is F. We already know that there is a gravitational force because the object is a mass. We know that there is a normal force because the object is on the surface. Since the object is sliding down, that is the direction of motion. If the object is sliding down the incline, then the frictional force will be in the opposite direction, which is up the incline. So both your applied force and the frictional force are acting up the incline. Now, this is a picture that will help us to answer this question, to calculate this magnitude of the applied force. But before we do that, we need to draw the components of the gravitational force. Fg perpendicular because it's perpendicular to the surface, and Fg parallel because it is parallel to the surface. And we are going to apply the fact that the net force acting on this object is 0 since it is moving with a constant velocity. So our opening statement would be the net force acting on this object is 0, but only after we have drawn the free body diagram. The direction of motion, we are going to take that as positive, so that these two, which are in the opposite direction as the motion, are negative. So I've got Fg parallel in the positive direction. We've got the kinetic frictional force in the negative direction. We've got the applied force in the negative direction. All of these, they add to 0. And remember, to calculate this Fg parallel, the formula is mg sine theta. This formula will not be provided to you in the examination, in the question paper. You need to know this. So we need to know that Fg parallel is mg sine theta. Fg perpendicular is mg cosine theta. So we need to know this. Fortunately, in what we have done yesterday, I've included those formulas for you. So we find them in that document. And also, when we're doing Newton's laws of motion, when we started, we also included those formulas. So revisit your Newton's laws of motion to find some of these formulas. As we proceed, we are given the mass of an object is 100, the angle of inclination is 25 degrees. So this is 100 kilogram object, that is 9.8, and this is the sine of 25 degrees. We were given the magnitude of frictional force, but it's 266 newtons, if you remember. Frictional force is 266 newtons. So we substitute it directly, minus 266. We can take this applied force to the right-hand side, so that it's positive. And then in the difference between these two, the magnitude of your applied force. And what is the answer there? Someone with a calculator, please assist. Anyway, can you assist us there? 148,166. Thank you, Cindy. And you have done, that's a magnitude of your applied force. So notice that what we have done here, we have drawn the free body diagram, even though they did not ask you to draw it. But part of the techniques that we have discussed here, the strategy that you applied, drawing a free body diagram is our very first thing that we're going to do. So we had to draw that free body diagram because it becomes like a compass. It's what guides us. It's what we use to zoom into the problem. It's what we use like to navigate through this, as we have seen here. That once we have the free body diagram, we're able to see which forces are in the positive direction, which forces are in the negative direction. So it became so much easier. It's very important, whether they have asked you or not to draw the free body diagram, just draw it because it will help you. If the block is released from rest without the force F, listen to what they're saying. If the block, now they're saying without the force F, is released from rest, the block is released from rest. Without the force F being applied, it moves 3 meters down the incline. It moves 3 meters down the incline. Look at that. It moves 3 meters down the incline. Calculate the speed of the block. Calculate the speed of the block at the bottom of the block. So we've released this from rest. Initial velocity is 0. They want us to find the final velocity. What will be our final velocity? And how can we answer this question? So let me open a new page. This question will come forward. How can we answer that question? Now we need to draw a new free body diagram. And this free body diagram now is without the applied force, because they've said that if the block is released from rest, without the force F applied. So we are now no having the applied force, but we are now having only 3 forces. This is your kinetic frictional force, that is the normal force, and that is a gravitational force. Are we given the height? The answer is no, we were not given the height. We were not given the height. However, someone might choose to say, but I can calculate this height, the height of this object. If this is 25 degrees and this thing is going to slide in a displacement of 3 meters, that's why they've said down the incline. I can easily calculate the height of this object. Someone may choose to say so, that even though I am not given the height, but I know that I can easily calculate the height. How so? Height divided by 3 is equal to the sine of the angle of inclination, which is 25 degrees. So let us look at that. Let's read again slowly. If the block is released from rest, the initial velocity is 0, because from rest means that it wasn't moving, it was stationary. Without the force F being applied, it moves 3 meters down the incline plane. It moves 3 meters down the inclined plane. Calculate the speed of the block at the bottom of the inclined plane. That is precisely what you're going to be doing. So what do we do here? We have calculated the height. And after calculating the height, we look back again at these conditions we have set at the beginning of this session today. We have said that when I have the height and there is a frictional force, applied force, we have said now it is no longer there. So we don't have the applied force, but I have the height, I have the frictional force. Then I can apply the formula that says work done by all the non-conservative forces is equal to the change in kinetic energy plus the change in gravitational potential energy. I hope you guys are seeing what we're trying to achieve here. Okay, we're gonna do this problem in 2 different ways. One is by applying this formula. because frictional force is the non-conservative force. And remember, they've said without the force F being applied. So we are eliminating the applied force. We are only left with the frictional force. So therefore, I've got the work done only by the frictional force. Since I've eliminated the second non-conservative force, which was the applied force. Otherwise, we were going to say, plus the work done by the applied force, because applied force is also a non-conservative force. But by eliminating that, we are only left with the work done by the frictional force. And remember what I've said to you, this is the change. Notice the patterns. Notice the patterns. So notice the patterns. So at the top of the ramp, at the top of our ramp, this is the initial velocity. That is the initial height. We're just going to copy this as it is. Initial velocity, this was listed for first. Final velocity, at the bottom of the ramp, the final height will be 0 meters because you are at the bottom of the ramp. At the bottom of the ramp, where in the height is 3. So we're at the ground level, that particular instance. So we've got your applied for work done by the frictional force, which would be equal to the magnitude of the frictional force times the displacement times the cosine of the end. Similar thing as what we have here. And these are the patterns that I need you guys to pay attention to. These are the patterns that I want you to observe when we're solving these problems. So our frictional force, they said it's 466. This will move a displacement of 3 meters down the incline. Frictional force is always at an angle of 180 degrees. So that one we shouldn't have any problem. It is always at an angle of 180 degrees to the displacement, and that is because it is in opposite direction. The mass of our object is 100 kilograms. At the top, it was released from rest. 100 0 squared. So that term we can forget about. The final height 100 9,8. Final height is 0 at the bottom of the ramp. The height is 3 minus 100 less gravitational acceleration as well as the initial height. Remember, initial height we've calculated and found 3 sine 25 degrees. We are trying to avoid having to round off so many times. So we're trying to avoid the issue of having to round off. That is why we just left this height here as 3 sine 25, because otherwise you're going to write the irrational number, and then that will affect your final answer in turn. The more you round off, the further away you get from the answer. So I need you guys to assist me once again. Forget about this because it is 0. Forget about this because it is also 0. So let's forget about this because this is 0, this is 0. They are both multiplied by 0. So we can just eliminate them out. And let's start with this side. 266 times 3 times the cos of 180. What do we get there? What do we get? 8, 9, 798. Am I correct? Negative 798.
Yes.
Right, let's go this side. This side, we're gonna start with this half of 100, that is 50 F squared. And then we've got this negative 100 times 9,8 times 3 sine 25 degrees. Can you assist us with it, one? Can you assist us with this negative 100 times 9,8 times 3 sine 25 degrees? What is the answer there? Now, guys, this doesn't take even a minute to punch on the calculator. Shouldn't take more than a minute. You just punch this on a calculator, you read what is on the calculator, you type it down, or you read it out. Because you waste this card, just really are wasting time here. You should be doing a lot of serious things. But we are waiting for someone to just give us an answer of this. That's a waste of time. 1, 2, 4, 2,5. Is it only comma 5? It cannot be comma 5. We need more than one number after a comma, Lindy. We only round off the final answer. Give me all these numbers after a comma. I want all these digits after a comma. We only going to round off the final answer. It's still not 49. All the digits after a comma, Lindy. All the digits after a comma. I need all of these numbers after a comma. Can't be 49. It's an irrational number. I need all of these numbers after a comma. Is this cut this up?
So,
Then we divide both sides by 50, and we take the square root. So that this cancels the other 50. That becomes a deficit. What's the answer?
Two comma 98.
2 comma? I'm still waiting. 2 comma 9 what?
2,98.
I don't know if maybe you've got a problem. Now, maybe you can't read the numbers what, but you're just wasting time, people. Just to read the number from a calculator is a problem. Can't you read the numbers? 2,98. That is one way of doing this. The second way, option number 2 of solving this very same problem, is to look at the work energy theorem. To answer this question 3,4. You can look at the work energy theorem. Work done by the net force is equals to the change in kinetic energy. Again, still gonna need your free program so that you can look at which forces are doing work. We've got your gravitational force, definitely this one is doing work. We've got the normal force, work done by the normal force is always zero. We've got your kinetic frictional force. So there are 2 forces that are doing work here. With the exception of the normal force, the other 2 are doing positive, non-zero work. So we've got the work done by the frictional force, got the work done by the gravitational force. And here we've got the change in kinetic energy. This is another way of doing this. If you were there yesterday, you have said to me that when this object is sliding down the incline, when the object is sliding down the incline, there is the displacement because the object is sliding down the incline. Then this angle between the displacement and the gravitational force, between the gravitational force and the displacement, there is the angle there. And this angle, if you look at it, this is 90 degrees, this is 45. That angle between the gravitational force and that will be 90 degrees minus 25 degrees, and that is 65 degrees. So that is the angle between these 2. Frictional force, remember, frictional force is at an angle of 180 degrees. But now, the work done by gravitational force, which is mg In this case, that is the magnitude of your gravitational force, multiplied by the displacement, multiplied by the cosine of the angle between the gravitational force and the displacement. And like we have said, that angle is 65 degrees. You get that. Plus 25 degrees, plus some of the interior angles of the triangle, and so plus 90. This is 90, this is 25, that is an angle. So when we solve this 180 minus 90 minus 25, that becomes our angle between the gravitational force and the displacement, and that is precisely 65 degrees. So this is why we've got this 65 degrees over there. And the 65 degrees is the angle between the gravitational force and the displacement, as you can see. The green vector is your displacement. The blue vector going vertically downwards, that's the gravitational force. Between those two forces, vectors, there is this angle over there. And that is the angle which we have set is 65 degrees. And then change in kinetic energy, half mv squared minus half mv squared. So this is the second way of doing this. And then we can easily substitute frictional force, 266. Displacement, 3 meters. Force, 180 degrees. Mass of the object, 100. Gravitational acceleration, 9,8. Displacement, 3. Force, 65 degrees. Mass 100 BF squared. It started from rest, so this will be 0. Initial kinetic energy of the object is 0 since the initial velocity was. And there you have it. We expect that this answer here will be something. 50 BF squared. I don't know what this answer is, but you guys can assist me with that. You guys can assist me with that. We know that this will be negative 798, and this will be, it will still be that number 1242,49. Definitely. If we are to believe in the laws of mathematics, then this number would be 1242,49. And then we can easily divide both sides by 50 and take out the square root. So that square root cancels the square, and you are left with just that. If your answer was correct, then this should still be 2,98 meters per second. So that will be the situation right there. Chinoni, that will be the situation. Your networks are very troublesome today. I can see that most of you are struggling. Cindy, now at some point a problem. Lindy, when we are under Chinoni, the network is bad today. But maybe it's because of the weather. So please go through this before you start to solve the problem that I'm going to be giving you. Before you go on to do question 4 and question 5. Question 4, question 5, question 6. Before we go to this question 4, 5, and 6, revisit our questions that we've done. Question 1, which we did yesterday, question 2 and 3, which we've done today. So please, before you go into solving question 4, 5, 6, be careful with your question 5. So be very careful when you arrive to this question 5, especially 5,4. Be very careful with it. Draw a free body diagram and calculate first the magnitude of the frictional force before you calculate this work done by the frictional force. So be very careful. Read, understand, try to solve. Before we go, guys, I've got Sissi. She wants to ask you guys a few questions. So please hang in there. Yeah, she's our colleague, and then she just came to visit you guys and to check if we are doing what you say we're doing. Should I leave you with that?
We can stay. It's not a problem. We requested.
Yeah, there is a
Morning, everyone. How many are there? 4.
There are 4.
4 on the line. Yes, my name is Meme. So I work for a company called Bonnie Trump Consulting. We were contracted by Sasol to basically do an assessment of the programs, the different programs that are offered at OCD and other stakeholders. So I know it's Project A, it's this program, the online learning. So what I would like to get from you is just a feel from you of the project, like the program, sorry. Has it changed anything? Basically, the impact, but maybe let's start from the beginning. If you can tell me how many classes you've attended. Do you attend all of them? Do you try to attend all of them? Why do you miss some of them? Or have you missed some? And then maybe just like you missed some years load shedding or whatever problems with technology, network. And have you seen a difference since you started the program? Have you seen any improvement? And is there a structure maybe for you, a structured program like every day, every time you attend the lessons? Or do you focus on problem areas? Just the feel basically. And also maybe that's tied to why you missed class. I would also like to know your learning environment, your environment. Like, is it conducive to learning? Is it conducive to helping you improve? And do you think these lessons are going to help you further your studies or reach your goals? So I don't know if you remember all of those, but yeah. If you don't mind, I just want to write down your answers so that I don't forget them. Also, just to tell you, or I can use my phone to record. That's totally up to you. If you want me to, if you don't, I don't have to do that. The thing is, when I report back to Cecil, I don't give them names. I just say maybe there were 3 learners online, and this is what they said. So because they at least need to know the impact, is it changing your lives? Is it doing what it's said it would do? Is it helping? They need to know that. And that I didn't speak to random people, and I spoke to you guys that are on the program. So that's why. So they let me know. I'm just sitting over here.
Okay, I hope you guys got the questions there.
I can take it.
Anyone else maybe is asking you guys, how are you finding the program? And also, if the environment from which you are working is conducive to learning, are you in a good space to study or to learn? And what are the challenges that you may encounter? And if you were not able to attend some of the sessions, what was the problem? Could it be a network or anything for that matter? So you can type in your answers if you want to. You can type in, then we'll check under the chats over there. And then, yeah, those persons maybe needs to take these answers back to the people who are funding this project, so they need to know.
Send them the recording of the classes. So what they can also.
Yeah, we upload it to YouTube and then we send them the link to.
Oh, nice.
Okay.
Oh, this is the
Question. Okay.
Okay,
All right, I will do so.
okay. Maybe, do you want me to take it?
Okay, I'm going to get my notes so that you can tell from the.
Oh, okay.
It's my notes. I think we use the chat option.
Okay.
Let's keep all this. It's sometimes.
Oh, okay.
So they manage.
I think yes, much.
Okay.
Okay, are you in?
You didn't see all this. It's still busy. I haven't. Yeah. Really? No, I'm sorry. So they only saw which question? Let's not type in.
That's actually the same as to one sentence.
Okay.
Oh, okay. It can be changed from these units.
Yes.
Always contain. Same way. It's still in the case of should be. Then we realize it.
Okay.
Experience people and 0 to 5.
Okay. We just do this now then, let's go to okay, this.
It's just personal.
It's amazing science.
That's really good.
You have something?
Good. I think all of this from the
Yeah, yeah.
Yes.
This time. Need to get it from children. It's the way.
That's it. It's a new response from the
That's it. Thank you so much. And thanks to Wayne as well. For your answer.
Okay, guys, I'll send you the homework, and then it's tomorrow. We're gonna meet tomorrow at 9, so we're gonna be doing that homework. I'll send you the questions. I can send you the questions in the with energy and power. So when I get to the office, I'm sending you the questions, and then we do question 4, 5, and 6 under work, energy, and power. So let me do it now. We're gonna be doing question 4, 5, 6 with energy and power. We send these questions. So this work, energy, and power, this will be a series of questions which covers your power and giving the definitions. So we're only gonna be doing question 4, 5, and 6. 4, 5, and 6 under work, energy, and power. And then we submit tonight before the end of the business day. So please submit your homework, and then we meet tomorrow at 9 again, 9 o'clock tomorrow in the morning. We meet to discuss those questions 4, 5, and 6. Do them, submit them today, tonight. And then tomorrow we meet, we discuss. I'll try to mark your work and send it back to you. Otherwise, we are done for today. Thanks for your time, guys. And let us meet tomorrow, please. Question 4, 5, 6. I've already sent the questions to the WhatsApp group. Question 4, 5, and 6. That is what we're going to be doing as our homework. Okay, otherwise enjoy the rest of your day. Thank you and bye-bye.